Welcome back! I just want to highlight I didn't feel any spirit in that just now. So there we go. Now we do. All right. So yesterday we talked and we did that lab. I've been bragging about the fact that everybody came close to gravity yesterday. I think that's awesome. We started this on 9/25. Today is the 27th. So if you are watching this video, Abigail, we will go ahead and have you make up the mini lab or run through it with you when you get back. Yesterday, is this the last thing we ended on? Okay. Now, here's the crazy thing that happens. Any two objects in the universe are impacted by gravity, which means if we had a universe that everything other than a marble on one side and a marble on the other side, it's almost zero, but there is still gravitational attraction between them. Give it enough time, an infinite amount of time, no matter the distance, they will eventually meet each other. With the understanding that probably not because our universe is expanding, but that's a whole bigger can of worms that we need to look at. Okay, now as we look at variations in free fall, gravity is close or strongest when you're closest to the center of the Earth. Okay, so it makes sense that on the surface gravity is stronger than it is out in orbit around the planet. Okay, beyond that though, here's just some pretty crazy things. The distance that you are from that center can vary wildly depending on where you are on the planet, what sort of region you're in. Like, if you're on a mountaintop, are you closer to the center of the Earth than somebody who's at sea level or farther? You're further, right? Now, do you think it's noticeable difference?
Yeah.
So, kind of. Now, we won't notice it just on an everyday basis, but just two little places here. And you don't have to include this, but I do think this is a really interesting fact. What's the value that we're going to use for gravity? 9.8, and depending, be careful, you might want to make it negative because it pushes you in towards the center of the planet or downward from your perspective. So just, I don't know if they're really fun, but I consider them fun. In New York City, the acceleration due to gravity is 9.81 meters per second squared.
Why is that?
What's up?
Why is it 0.11?
So it's just more precise. Like if we would have had better measuring, we might have gotten 9.81 out of here yesterday. Okay, now, anybody in here have been to New York? Okay, can you see the ocean when you're in New York City, like in Manhattan? Okay, so you might not remember, but you can, because the Hudson Bay is right there. New York City is at sea level. Denver has a common name. Anybody know the name for Denver? Or its elevation? It's a mile-high city because it's a mile high. Like that's the elevation in Denver. In Denver, being the fact that it's a mile high, it's further from the center of the Earth, right? So when you actually take precise measurements, the Denver's gravity in Denver winds up being 9.79 meters per second squared. Now, this is like pretty insignificant just in this grand scheme, but I'll tell you, gravity does impact more than just how fast things fall. I'm not going to test you on this right now, but how much gravity there is and what the force of gravity is dictates how time moves. So the more gravity that you have, time moves differently than less gravity. What that means and why we matter, or why it matters to us, is this difference seems so small, but if I'm using GPS stuff to try to calculate where I am, and it needs to keep track of my position and time and velocity and time and all those things, if we didn't account for these differences, or the difference in the satellite that's orbiting Earth much farther away, our satellites would be wildly off, like within a month. Our GPS would be garbage, it wouldn't work, because it has to account for the difference in gravity, which changes how time flows. Okay, now, with that, pretty wild, huh? Where's the tallest place on Earth? Mount Everest. Do you guys want to do a quick Google search for one more fun fact? Top of Everest, and I don't know the real name of Everest, we'll get it here in a second. Everest, if you want to include it, what was it? For the top of Mount Everest? Nope, sorry, I'm just going to write Everest. 9.77 meters per second squared. Cool. Now, as we go through this, we are going to start this basic idea first. We do have launchers, if you guys have never played with them, that like are spring launchers that we launch steel balls at a given angle and stuff. We'll be launching stuff at moving objects, trying to hit it. We will get there. As we go through, though, two little brief comments just before we get that. I want us to consider a situation that happens all the time. I want us to imagine real quick that I'm just going to throw something up, and not even imagine. I'm going to throw it up, and it comes down, right? I normally can catch. I don't know what happened there. Anywho, I want us to think about a ball thrown upward. Now, we're not going to take any real measurements with this, but we are going to be able to see a couple things that are going to show up over and over and over and over and over. Okay, if I were to launch or shoot a ball or throw a ball upward, right now its velocity would be 0, right? And then all of a sudden, it has an initial velocity once it gets rolling, like it starts picking up velocity because it accelerates upward. Now, the whole time this goes up, something's fighting it. Is the speed increasing or slowing down? It's slowing down. Why? What's that force that's fighting me?
Gravity.
It's gravity. Now, eventually, here we go. We throw it. It's slowing down, and inevitably it's going to come back down, right? Before it comes back down, though, what does it do? It stops. And if something is stopped, its velocity is what? 0. And then all of a sudden it starts going this way. We see acceleration or slowing down, negative acceleration on the way up, and then we see that same acceleration on the way down. So as we look at this, there's two perspectives that I want us to think about. I want us to consider the following. Two little graphs. We're going to have time in seconds and position in meters. And I'm not going to put values on here. I just want to think about this. Position in meters. Or you can think of this as the height of your object, whatever you want to imagine this as. Now, we know that there's a lovely formula that says, hey, if your initial velocity is 0, it's 1/2 at squared. Like, this is what Galileo's big idea was that led to us being able to do these things. This looks weird when I write xf equals 1/2 at squared. Now, don't write this part down, but I just want to pull in a little bit of math in here. If instead of writing this, which I'll write this first, xf equals and 1/2 at squared. Let's just pretend that's what it is. This, can you tell me the parent function of this model? Maybe you can, maybe you can't. Okay, I'm going to make this look mathier, and you guys are just going to tell me what sort of function we're looking at. If I just word it that way, can you tell me what sort of function this is? So it's going to look like a parabola. If I write it like this instead, and 1/2 of 9.8 is 4.9, if I did this, is it more clear that we're very obviously working with a parabola? Like, this is a quadratic, right? And since it's a quadratic, it will have a parabola. Which this is going to tell us our position then, when we draw this graph, it has to look like a what? It's a parabola. This is no different than 4.9x squared. It's just t instead. Now, as we think about this then, I'm going to sketch really roughly this graph. Well, our parabola for an, like if we toss an object up and we think about its position, what would your initial position be? 0 probably, right? Like, you get to pick it. Then it goes up to some position and comes back down. Now, time also passes with that. Anytime you're dealing with a ball thrown or something launched like this, we are going to get this lovely, lovely parabola. Every time. Now, this can be really misleading. And I want to cover where these things get misleading. How did I throw this? Did we specify? So there's a couple things that everybody gets goofed up on. When I look at this graph, my first gut feeling is this is what happened. Because I can see that path that goes, it's like a parabola, right? Is that what we're talking about here, though? No. When we just throw an object up, straight up, we're not following its exact path. This isn't its actual trajectory that it follows. This is just its position increasing, increasing, slowing down due to gravity. What happens here? It stops, and then it does this whole thing. Now, as we look at those, will you kick that just forward? I'll grab it underneath my desk here in a minute. Okay, as we look at this graph is certainly worth looking at and being aware of. Motion travels in this, or throwing objects travel with that trajectory. Oh my gosh. Vertically thrown objects look like this when we graph them. All right, beyond that, I want us to think about this other little piece, and I'm going to just put a couple dashes on this first graph. But we talked about position versus time, and then what, do you guys remember what the next little extension was? Position versus time was okay, but we did cooler graphs after that. Velocity in meters per second. So the good news is that in here we get to ignore air resistance, like every time. I'm going to put 3 dashes on this graph, and I'm going to put the same 3 dashes over here. Let's say we started at t naught, or t sub 0. The peak happened at t sub 1, and we finished at t sub 2. Those are the times that I'm checking. T naught, or t sub 0, my initial time, T1 and T2. Okay, I'm going to put the same 3 marks over here, and I'm going to have to change my graph, and I'm super sorry. You guys are going to have to change your graph as well, and you can probably tell me why here in a second. For the first section from T0 to T1, what is the velocity? You can't give me a number, but you can tell me something about it. How would you describe the velocities, I don't know, on this whole section? Say it again. I heard it. I mean, I heard it again, but I don't know who's saying it. Are people whispering, or am I hearing stuff?
I think someone's saying something. I'm not saying that.
Somebody said something positive, maybe. It might be what I heard. Somebody said it. I don't know who. Okay. Why? How do you know it's positive? Convince me. At this point, how do you know velocity is positive? Okay, I'm going to make it math here, but you're absolutely right. What's the slope of that? Positive. Yeah, I can see it happening. Now, all of a sudden, what's the slope here? What was wrong with this graph that I drew for velocity versus time? If you have just first quadrant, what don't you get to see? You don't get to see any negative velocities. So, terribly sorry about it. I'm going to do this, though. We'll have the same thing. T0, T1, and T2. Okay. As we look at this, the instant I release it, that thing is traveling upward the fastest it's ever going to travel. Guaranteed. So let's just say this is where it starts. While we're looking at this, at T0, we'll just say it has this initial velocity, however fast we launch this thing up. What's its velocity at T1 if we look at the position versus time graph? 0. That's the max, right? If you were to draw a line that touches it just once, you're going to draw horizontal, which means I need to go through here, I need to go through here, and this is just kind of an interesting idea. If I throw it up at 10 meters per second, it'll take roughly 1 second to go up, and then it'll take roughly 1 second to come back down. Okay. How fast will it be going when it gets up? If I throw it up at 10 meters per second, when it gets back to my hand, how fast will it be going? Any gut feeling? 10 meters per second. If there's no air resistance, exactly as fast as it went up, because the only thing acting on it at that point is gravity. Which means if I try to come down here, and I'm just going to eyeball this out, that looks like the same. Here is our velocity versus time graph. Now, I see that on this section, and you can include these if you want, this section right here, slowing down, or negative acceleration. What happens at this point? Stopped. And then what happens on this whole section? Speeds up. Now, just to kind of reinforce some things that we've already talked about, if we think about this, in this context, are we treating acceleration as a positive or a negative? So I want you to discuss with your neighbors, just so I don't quietly wait and stare and then answer the question because I inevitably feel uncomfortable. Talk with your neighbors, decide if this is positive acceleration or negative acceleration, and furthermore, try to justify it. Okay, as we're looking at this, do I write acceleration anywhere on these graphs yet? Not explicitly. However, I do think it's implicitly in here. The slope of a position time graph gives you velocity, right? What's the slope of a velocity time graph give you? Acceleration. Is this slope positive or negative? Acceleration is negative in this example. Now, as we go through, the reminder that I wanted to hit, right here, we have positive velocity and negative acceleration. You guys told me it was slowing down. When the signs are opposite, that's what should happen. Down here, we have negative acceleration and negative velocity. Same sign. It should be speeding up. That's what you guys told me would happen. I'm good with it. Okay. That was the end of the chapter. Cool. Nice. So, before I just cut you guys loose, I want us to work through a couple of problems together at least. So we're going to do some examples. I will take pictures. If I were you, I would just put them like in your notes. I would just say examples, and then I'll just list the page number. This is on page 78. And we're going to do a couple of them out of here. I want you guys to go ahead and open up your text to page 78, at least one person in your group. I will do a little editing magic here, and we will cook. Yeah, let me do it. It doesn't decide that I'm going to work now and not later, right? It's just always there. We know at the very top when this thing stops for that instant in time, the velocity, and we don't have like good times to label here. Subscripts are my best friend. You might learn to hate them. The velocity at the top equals 0 meters per second. I guarantee it. The acceleration, we could say at the top, and I will say at the top since that's what it's asking, but be very aware it could be literally everywhere. And it is literally everywhere. Anytime that you're dealing with something falling and gravity is the only thing acting on it, it is what? Okay, now we have to make a decision. I have no major issue but concern with this value. What did we say if we look at that last example? What was the acceleration in that context? It was 9.8, but there's a sign on it. Is this like the same context? So unless you want to say that our coin goes a negative distance up and then use positive acceleration, there's probably a better choice. This should be negative 9.8 meters per second squared. Okay. Does that make sense to why that's the case? Because if I have to measure my position, like my initial velocity, if we flick a coin up, do you guys agree it's in the positive direction? Now that's the most natural. Could it be the negative direction if you really wanted to? You could, but then acceleration would be backward. Like I could say I start at 5 meters and then I get up to 0 if I make that scale weird. It's a weird way to do it, but you could. Okay, on Bravo. Let's dig into that one because I think that one looks like a little bit more involved of a problem. Was Johnny Bravo a thing when you guys were kids? Or was he already canceled at that point? Okay, that answers that question. Here we go. We have a coin that reaches that point. I want to find its initial speed. So the initial speed, the instant we release it, is what it's asking for. Because this is going to be a mathy type problem, I suggest we do the standard mathy type problem style. What's the first thing we should write down? Knowns or givens. No. All right. What do you know?
The position of the highest place
Okay, how would you write that down?
X.
Love it.
Is it fine? It's fine.
I would call it final for this one, yeah. We know x final is how high? 0.25 meters. Now, I left an awkward space there for a reason. If that's what we're going to call our final position, what's our initial? 0. Good. There's one more value hiding in here, and it will hide in a lot of problems like this. They don't specify, but I think it's pretty safe to assume. Weird. Where do you think they're working? Are they working on Jupiter right now? They're probably on Earth. Why am I specifying that? Gravity. Man, we know the value of gravity here. What's acceleration due to gravity on our planet? Okay, within this context, though, same issue. Negative. Cool. All right. There's one more piece of information that we know that might be worth including. We're trying to find its initial speed, and we're told the highest point. Do I know anything about its speed at the highest point? Its velocity. I hate that they use speed. Oh my goodness. VI is also 0. Whoa, whoa, whoa. Am I right or am I wrong? There's one little change. I'm not going to erase stuff. I just lied right to your faces. I'm wrong. Why? It's my final velocity. Okay. We got that. What are we finding? Initial velocity. Now, thanks to this brilliant system and this cool guy, we have these formula. You have these 5 formula. I'll go get white paper as soon as I remember. It'll happen eventually. I need a position, or I need a function, an equation that relates position, acceleration, and velocity. So let's see. Velocity, velocity, acceleration, position. 1, 2, and 3 are all fair game, seemingly. Could it be this one too? I don't think so.
We don't have time.
We don't have time. Okay. Could it be this one? No, because again, we don't have time. So, 1, 2, and 3, remember these are really the same equation, just rewritten. which of these would you like us to use to find the initial velocity? I'm going to use the first one, and then we're going to have to do a little bit of, we get to do a little bit of mathematics. So here we go. Equation and work. I know that the final velocity squared is equal to the initial velocity squared plus, lost my spot, 2a delta x, or 2a xf minus xi. If you have these equations, nothing that we do should be crazy. I'm hoping we get to do a little bit of factoring here in a minute, but we'll see. Cool. What are we actually trying to solve for? Initial velocity. Do that. I'm going to rearrange and then solve it. I'm going to give you a head start. If it's more natural for you to plug it in and then solve it or rearrange it, I'm cool. Don't matter. I'm going to give you guys a head start. Solve for me initial velocity. The same thing. As I look at this, anytime I take a square root, what should I do? What's the square root of 25? That's credit. I heard 5. Negative 5 is the other one, right? So I have totally disregarded seemingly the plus or minus that should go in front of this radical. Why? If we're flipping a coin, we've already decided that position is going up, right? It's a positive direction. Our velocity is going to be what? Positive. So I don't even have to consider the negative side of it. Contextually, it doesn't make sense to say it would be negative. Okay, at this point, I'm just going to plug and chug. We get, on my work, the square root of, I think we can probably do this. What's VF? Okay, so we're going to take 0, we're going to square it. We're going to subtract from this 2 times, what's acceleration? Love the fact that you specified negative 9.8. Times, what's our delta x, or xf minus xi, if you want to write it all? 0.25. If you wait until the very end to solve stuff, in my opinion, and this is, for me personally, I avoid mistakes. Because if I have to write numbers, I move decimals, I do wonky things. Don't know why. In any case, you should wind up taking the square root of negative 2 times negative 9.8 times 0.25. I don't have a calculator sitting in front of me. Somebody hook it up. Can you say that like 3 decibels louder? 19.6. Can I get a second? Oh, somebody might have got a different number. 19.6?
Yeah.
Okay. Would you like me to do this with plugging in first so we can see if you made a mistake somewhere where it happened? Okay. So, this feels super unnatural. Is that what you got, Fern?
I got 4.9. Yeah, I got
Okay, I got it.
Why would you say yes?
Because
I didn't type it in. Let's check. When you typed this in, you got that?
well, I did it differently.
Ah, you didn't take the square root. Somebody.
We did the 2 times 9.8, which is 18.6.
And then you multiplied by 0.25?
Yeah.
And then you took the square root?
Well, no, I didn't read it.
Okay, so we'll just let me grab a calculator real quick. Can I borrow your calculator?
2.2 times 9.8 is 19.6.
Yeah.
And they just forgot.
Ah, so you just didn't finish the problem. That's okay. So we're going to check real, or not real, different answers. 19.6 times 0.25. 2.21?
What?
2.21. Because I've done everything. I did the square root of everything. And I'm sorry, you might have just given me the different answer. Let's plug it in and see where other issues might have happened. I already forgot the number, 2.21. Okay. If you decide to plug in first, that's all fine and dandy. Did everybody plug in right from here? Or did you solve it for VI and then plug? Probably here. Okay. Just in case. Either way. Let's check it. I'm going to use this orange color. What's VF? Okay, so we have 0 squared equals VI squared plus 2 times negative 9.8 times 0.25. Okay? And then, if depending on your amount of work that you show, you might have 0 equals VI squared, negative 19.6 times 0.25. I don't know what that is. 4.9? Okay. Then you would add 4.9 to each side. We'll take the square root of the left and the right, and we should get 2.21. Now, I've skipped steps in this part right here in the orange. I skipped a couple that I didn't write down every literal step like I did here. It looks like yellow's more work. It'll be hard for you to convince me that yellow's harder. For me, like that's personal, right? Like you can do whatever you want. Give me a context. I'm not going to write the sentence, but I want help with it. One person to give me this context. Let's see. You looked at me. Can you give me this context? Meters, but otherwise I love it. The coin is flipped upward at 2.2 meters per second. The initial speed of the coin is 2.2 meters per second upward, however you want to word it. Okay, now we get a more fun problem, I think. If we catch it at the same height, how much time did it spend in the air? Okay, so this is still a math problem, right? Except now we get a little bit more information. I'm just going to copy and paste because I can. I know all this stuff still. Those are still all my initial conditions, my given information. We just got one more piece of information that might be of value to us, though. All this still applies, and what else?
Stops at 0.
So it stops at 0. That's okay. Here's my suggestion. I'll go up here. I heard velocity. Because all of a sudden we know all this, but we also know the initial velocity. Now, if I just copy and paste, and that's obviously what I've done, I want to make sure that we see exactly what this problem is telling us. If we say we start here, and here's our coin flip, right? So I want to throw something that won't break. Here's my coin. I flip it up, and it comes back down. That's the whole trip, right? Up to this point, we're only here. We've only dealt with half of it because we still have our initial position and our final position ending up here. If we solve this somehow for time, we've calculated how much of the time. So notice what happens. I'm going to flip it. Here's the whole trip. Okay, right? That's the whole one. Right now, though, based on this, that would be xi is 0, xf is 0, and we just would get 0, and things would be tough. However, we're doing this. How much of the trip have we covered so far? I heard you say it louder, Nick. You whispered it. Somebody over here whispered it. Somebody said half. Claim it. Cool. All right, we're doing half the trip, which means whatever time we get from this information, what are we going to do with it afterward? We're going to double it. Okay, so now we have all this. We're trying to find time. Find time. I need an equation that relates velocities, accelerations, positions, and time. Well, I know which one I'm thinking I'm going to use. You guys?
5.
So 4 would work well. 5 would work well if we do a little tweak of this problem. Do you know? Talk with your neighbors real quick. If we want to use 5, I'm down with it. That's one I would prefer to use. But you got to be able to tell me what we need to change to be able to use it. If we want to use 5, VF equals AT plus VI, we need to change something. I'm going to give you a moment. I need to know what it is because one of these needs to change. We'll go with number 4 on our list, which is this lovely... It's an XF, right? Yeah, okay. X of F equals X of I plus VI T plus 1/2 AT squared. All right. Because most of you would probably just plug in values, let's do that. I want you to plug in values for me, and inevitably we're going to reach our Algebra 2 prereq noticing thing. I'm going to give you a minute. When I plug in and rearrange, this is what I get to. Now, I rearrange for a very specific reason, because if we think of algebra, you probably don't want to have c plus bx plus ax squared. That feels wonky. You always put the x squared first. Okay, here's the cool thing about this. This is not a math class. Okay, let me rephrase. Here's the sad part about this. This is not a math class, which means I don't think I should necessarily make you guys use a quadratic formula to solve this. Alternatively, you all have these super fancy computers on your desks in front of you at this point in time. They're called calculators, but they're computers nonetheless. How could you use your calculator to solve this? Love what you've done. Can you tell everybody the first button you pushed? Riley went right to graphing this, or at least putting in the equation. Good. Put this into y equals on your calculator. And I'm going to type it into my calculator, and we'll look at my screen here for a moment. I would rather just use a quadratic formula.
Do we use X?
What do you think?
It would be X, right?
I would use X. I will. You have to, yeah.
Oh, there's a T.
Yep. Just how do what? So check it out. There is an X and a T, certainly. However, the X and T, those are just independent variable, right? So if I were doing this in math, this equation would be 0 equals negative 4.9 independent variable squared plus 2.21 independent variable minus this. Just use X on your calculator. I'm totally good with it. Okay, so I'm going to type this in, and I'm going to slide the screen over just a skosh so I can see both simultaneously. So here we go. All right. Whatever. Negative 4.9 x squared. Lost my spot. There it is. Plus 2.21x. Minus, bless you, 0.25. Okay. We have it graphed. Cool. I'm going to go to my graph, and my window is nice right now. That's what this parabola looks like. Tons of meaning there, huh? Not really. So, right now, can you even tell? Does your graph look exactly like this? Okay. Oh, I like yours more. Couple things. I can't see what's going on because everything that I'm worried about happens right here. How do we adjust the screen here? Okay, you can zoom. There's a zoom button right here. And I'm just going to zoom in. And I want it to be centered. I'm going to move a little bit to the right. I don't know how far to the right. We'll go there. Did that really do it? Not particularly. Now, here's the cool part about this. If we're just looking at this function as it is right now, can you tell me the highest value on the y-axis you're ever going to get? Okay. Why? This is the position versus time that we're seeing right here with everything else worked in. Is it going to be 0? Okay, so let's check this out. We're going to keep rolling with it. There's something on this graph that matters to me. When we're solving this equation right here, what are we actually looking for? I'm looking for the time. Now, mathematically, if you're solving a quadratic and x squared something, you set it equal to 0 like all the time, right? Because you're looking for the zeros, the roots, the solutions, the intercepts. Is this still a quadratic? Are there solutions, roots, zeros, intercepts, you think? Okay, so a couple things that we're going to try on this. If we go into this, do you guys know how to get your calculator to give us values of stuff? Say it again. Second table. You can look at these values, that's fine. Now, as I'm looking, I see that nothing ever comes up here. And all of a sudden, I'm trying to decide just real quickly if we have something wonky. Initial velocity here, final velocity. Didn't need it. I'm cool with that. 1/2 AT squared, blah, 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 blah. Okay, there's something goofed up. Is that okay? Like, might it happen to you as well? So we're going to spend just one moment. We may abandon and just talk about the easier way to do this, because I don't see where the mistake is. If anybody does, I'd love to hear it, but I don't see it. So position, 0, because we don't see the roots. Now, we're going to not erase, first of all. I'm going to do this real quick and just say easier option. And we got about 40 seconds. I'm not even going to give you homework this weekend. That's okay. Check this out. Do you know the initial velocity? It wasn't 0. It was 2.21, right? Do you know the final velocity at the end of our trip? Knowing that it leaves at 2.21, comes up. When it falls back down, how fast is it going to be going? Careful. It goes 0 at the very top. It accelerates that quickly. If I launch something upward at 2.2 meters per second and it comes back down, at that exact same point, it's going to be going 2.21 meters per second, but the opposite direction. It's going to be negative. You know final and initial velocity. I'm going to find my error. We'll discuss that and work this problem with this method on Monday. Later, Raiders. That took longer than I thought. Sorry about that. Or not, because now you don't get homework. I don't know. All right. Peace out, A-Town.